Okay, this is 8G7, 8th grade geometry, standard 7, video 2. We are working with the Pythagorean theorem in 3 dimensions. We've already talked about solving in 2 dimensions, and now we are going to be using 3-dimensional figures. Here are a few terms I'd like you to know. Write them down in your journals and define them. All right, the first 3-dimensional figure that we see here, this is a prism, and looks like we have some triangles on there. The base seems to either be a square or a rectangle. We're going to figure all that out, and it says that we need to calculate the height of the pyramid. All right, so if you're looking, this is a tough part to tell students to look at it 3-dimensionally. It's really how you are focusing your eyes on each particular piece of this figure, and it's going to take some time to get used to that. I will tell you I'm going to be going back and forth from my desktop to the board here, so forgive me for spending some time walking over here. All right, it's just easier to work the program from sitting here. Okay, so the first thing, if we are calculating the height of the pyramid, we know that when we measure our heights, we want to go from the highest point all the way down to the lowest point of the figure. Kind of like when you're measuring your height. What do? You probably stand up with your back against the wall. You try to not be on your tippy toes, and you measure from the top of your head all the way down to your feet where the floor is. Well, it's kind of the same idea. When you deal with these 3-dimensional figures, if you were to take the height of the figure right here and just kind of measure down the side here, we call this the slant height, over to this edge of the figure, you are measuring on a slant, and you never like lean over slanted as you're measuring your own height. So why would you do that with a 3-dimensional figure? All right, so if I am drawing in here this slant height, which is the line that we aren't going to use, it will be necessary for us because it's going to help us find that center point. That height coming right down the middle here will find the center of our 4-sided figure on our base, and I think it would be right about there. So we have this, let me see if I could draw in a little center point of the figure. Okay, so there's the height of your figure. Here's the height that's on a slant. And now if I were to connect those two, how is that going to look? All right, we've created this 90-degree angle right in here. Let me draw it for you. There's this little 90-degree box. All right, and once we've created that 90-degree angle, we should be able to use Pythagorean's theorem to generate this height of the pyramid. All right, so let's look at the information that is given to us. We have, I'm going to go back to the board now. Okay, we have some dimensions given to us, this 73 centimeters and the 96 centimeters. I'll draw a couple of little arrows here. All right, the 73 centimeters is relating to the slant height. That's one of the legs of our right triangle. And this 96 centimeters is actually relating to this base leg. That's this entire leg right here at 96 centimeters. Well, if I need to know what the midpoint is of our right triangle, and I'm in the middle, right? The midpoint is the middle. How many centimeters is the line that I'm drawing right now going to have to be? Okay, you're right. That's going to be half of this 96 centimeters. So what is half of 96? Well, that is going to be a 48 centimeter leg. All right, I believe we have all of the pieces of information necessary to find the height. So I'll bring over the theorem. Let's substitute in some numbers here. Okay, the hypotenuse, we see that slant. We always recognize the hypotenuse as the slanted line anyways. We know that that is going to be 73 centimeters. So 73 centimeters. And what are we going to do? We're going to square it. And then I have our a squared and our b squared. Well, a and b are interchangeable, so let's just call this leg down here b. So we'll have plus 48 squared, and the height, we'll call the height of this figure a, and that's what we need to find. So a squared. All right, we've been working with the theorem. We just have to substitute our numbers. Actually, we're going to calculate them using the calculator. They're quite large right now. And we have 48 squared. That means 48 times 48. That is 2,304. Don't be intimidated by the larger numbers today. The process is still the same. All right, 73 squared. And that's 5,329. All right, if we are solving this equation for a squared, we draw that wall all the way down. And to undo this adding 2,304, we would subtract it from both sides. So we'll take 5,329 subtracted by 2,304. See what we get. We get 3,025. And that should be equal to now a squared. And what are we supposed to do now to get a? I don't want a squared. I want the height of this pyramid. So we need to take the square root of both sides. So I have a quick button here, a little different than your calculator. And a should be equal to 55. And what's our unit? 55 centimeters. And that pretty much makes sense, right? Because the hypotenuse is the longest leg at 73, and we have our 55 and 48. Final answer, height is 55 centimeters. Okay, the next one is a real world problem. It says that Stephen is packing his things to move. He wonders if his 41-inch golf club will fit in a box that is 9 inches by 12 inches by 35 inches if he puts them in the box, if he puts this club in the box diagonally. Will the club fit? Okay, I'm going to go back to my computer. I'm going to have to be drawing in some lines here for you. Here's where it gets tricky. We're dealing with this three-dimensional box. You can see the front is more darkened than the back side. The back lines are a little bit more grayed out. So if I have the 3 dimensions, I'm going to quickly put those in where I believe they belong. You know what? I'm going to have to move everything over here. Now I'm covering up these dimensions because they've changed. I just took this okay, sorry about that. I took this off of the image site, and the dimensions don't match the problem that we had. So, okay, if I'm putting in the dimensions here, I have a 9 by 12 by 35. I can recognize that the 35 is the longest leg down here. So it's running on this edge. We have a bunch of 35-inch lines. Even that grayed out one in the back, we're in the third dimension here. Okay, so then the 9 looks to be like the smallest leg or edge. It could be the top, it could be over here, it could be this grayed out one. I think I'll just put it down here for today's purpose. That would be this one. And then the 12 inches is a little longer than the 9, and this leg is the remaining part. So we have our length, our width, and our height. That's what gives us our 3 dimensions. And we're supposed to fit a golf club diagonally. That doesn't mean that it's laying across the bottom or the base of our figure. It's actually going to be standing up from one corner to another. So I'm going to draw that in right here. And let's make it a little thicker here. So here comes the golf club. It's not on the base. It's going to have to stand up from corner to corner across the way. And the question is, if this is a 41-inch golf club, will it fit in the box that has these particular dimensions? All right, so in order to do that, we're going to actually, it's a two-step problem. We're going to have to determine the diagonal of the base of our box before we could figure this out. We don't have enough information right now, so I'm going to draw the triangle that is inside of this three-dimensional figure first so that you can see where we need to go with this problem. Okay, so we have our golf club, and then we have this triangle within the three-dimensional box. And let me bring down that third leg. Okay, I hope you can all see the purple inside. Now, in order for us to be able to determine this diagonal, or the hypotenuse we can call it, we're going to need to figure out what the leg is down here on the bottom. And I'm going to actually, let's see, can I color that a different color? Here, let's try that. Can I make that maybe a red now? Okay, so we need this particular diagonal before we can get the golf club. And now we're going to use the Pythagorean theorem on the base of our figure. So if this is one of our legs, I'm going to use the other information that I know, which would be leg down here. Notice the 90-degree box is going to help us out. And then the third leg of our first triangle. Okay, so again, this is very difficult to see maybe for the first time, but we cannot find the diagonal of the interior of a box until we figure out the diagonal of the base of the box. And we're going to use the Pythagorean theorem for the red triangle first. I'm going to head back to the board so that you can see that. All right, Pythagorean theorem. We'll use the red pen for the red triangle. This is the base. So we don't know the hypotenuse. That's this diagonal line. So we're going to go with our a squared plus b squared and set that equal to c squared. Well, a squared is equal to 81, and b squared, 35 multiplied by 35, and that is 1,225. That is equal to c squared. All right, now we're going to need this total. We'll go back to that calculator. We're going to add these two numbers up, plus 81. And we get 1,306 is equal to that c squared leg. 1,306. And that is c squared. So if this line right here is known as 1,306, I can either take the square root of it and find out what that c leg is, or I might be able to leave it as is. Let's see if it's a perfect square first, or if we're going to have to do any rounding. Okay, so it's not a perfect square. I'm going to leave it right now in that form, because when I do the purple figure, I can just keep it as that c squared leg. All right, so let me go back to my computer here. All right, now that we know this leg is known as 1,306 as the c squared, I'm going to need to figure out the rest of the triangle. So let's make that now all purple. Okay. So the dimensions I have are this 12 inches, and now I know that this is known as 1,306. I could take a root of it. I'm actually going to hold on for a second because I know I'm going to be adding those two numbers up. So now I'm going to go a squared plus that b squared is going to be equal now to my golf club, and we'll see if the golf club is going to fit. All right, let's go purple writing, and we'll head back. All right, using the theorem again, here comes the big finale. We have this 12 squared. We're going to add it to our new diagonal that we just found out on the base here, and that was going to be equal to that rounded decimal number, but we're going to keep it in form, which was 1,306. No need to square it because it's already in that squared form, and that should be equal to this possible golf club. We'll see if it even fits in there. All right, do some math here. We have 144 plus that 1306, which was already squared. Trusty calculator. We have 144 plus 1,306 equaling 1,450. Now it's time to take the square root. We'll see if this diagonal, when we take the square root of it, will fit the box. See if that golf club will fit in the box. So we'll take the square root of that, and we get 38.08 approximately. 38.08. So if we had to round up, the golf club would have to be less than 39 inches for it to be able to fit. Let's go back to that problem. And he says that he has a 41-inch golf club, and the diagonal in my box can only fit less than 39 inches. So X has to be less than 39 inches. So does it fit? The answer would be no. It would not fit in there because the diagonal right now has to be less than 39. Well, that was probably brand new for you. I hope you were able to pick up some of those concepts. The best part of this is you could watch that over and over, but bring all these questions with you to class. I'm assuming you may have one or two questions about that. So in your journal, define the given terms, maybe some new things that you learned, write those down, and then again, all those questions that you have, bring them to class, and we're going to do some more of these together.